Good afternoon, my dear students. My name is Dr. K.C.H. Apparao, working as an associate professor in mechanical department, Institute of Aeronautical Engineering, Hyderabad. Okay, in previous class we discussed the significance or the importance of dimension analysis. So why you have to choose the dimensional analysis method or process. So to form the dimensionless numbers, just like Reynolds number, Prandtl number, Nusselt number, these are. So we already discussed that one. So in convection process, just like there are so many properties of fluids are there. Like you know that density of the fluid and viscosity, dynamic viscosity, and kinematic viscosity, specific heat, thermal conductivity, and just like and so Prandtl numbers. So many parameters are there for the fluids. To study of these individual parameter or effect of individual parameter and physical significance of these properties on convection. So study of uh, effect of these properties on convection. So it is not easy to include to study of all the properties of fluid on the convection. So it is very critical to uh, study the individual influence of the parameters on the convection. So for that purpose, just like we have to convert these properties into some dimensionless numbers. Based upon the dimensionless numbers, so we can study the just like significance or importance of the convection of those parameters, just like those properties. So in previous classes, it means through dimension analysis, we convert the some properties into some Reynolds number, some dimensionless numbers, just like Reynolds number. So we already derived that one. So you know the formula of this one: rho u l by mu, or u l by just like nu, the kinematic viscosity. So this is the velocity of the fluid stream. Next to L is the just like length of the solid surface. Suppose fluid is flowing on a solid surface. So there are so many properties. So temperature of fluid is equal to T infinity, and solid surface temperature is equal to Ts, and that fluid properties are many: density, viscosity, dynamic viscosity, kinematic viscosity, thermal conductivity of the fluid. So thermal conductivity of the solid, that is different, and specific heat also there, and just like so this length of the pipe, you know that this one. So many parameters are there to for solving the convection process, the rate of heat transfer through convection process, just like it is also depend upon the all the these parameters. But it is not possible to study of the influence of each and every parameter. Then you have to convert the those parameters into dimensionless numbers. So what we taught in uh, just in previous class. So Reynolds number is equal to rho ul by mu, or ul by nu. Okay. So similarly, Nusselt number is equal to hl by k. So these are the length, and h is the rate of heat transfer coefficient. K the thermal conductivity. So these are the parameters. So in which just like by using these Reynolds numbers, just like dimensional numbers, like Reynolds number and the Prandtl number and the Nusselt number and Prandtl number also there. So by using these dimensional numbers or dimensional ratios, we can study the influence of convection. So for that one, just like we already some solve the some numericals also based upon this one. Okay. So in this class we will see the significance of these dimensionless numbers, just like significance of the Reynolds number. So what is the significance of the Prandtl number, significance of the Nusselt number, and the Strandian number, so ST. So we'll see the significance of these parameters or these numbers, dimensionless numbers, and the convection process. We'll see that one by one. We'll see. So because uh, to find the rate of heat transfer, so through convection, so it is depend upon the type of the flow. So either it is laminar flow or a turbulent flow. So based upon the laminar flow and turbulent flow, formulas are different, because we know that Nusselt is the function of Reynolds number and Prandtl number. We already saw that formula. So Nusselt is equal to C into RE to the power of A. So Prandtl number to the power of B. So it is C comma and A and B. So these are the constants that depend upon the type of flow, laminar flow or turbulent flow. So based upon the flows, so the C and AB values will be varied. So also just like type of flow, so just like flow through the some circular pipes, that is inner flow. So for the inner flow also, just like Nusselt formula will be varied. Okay, with respect to Reynolds and Prandtl number. And outer flow, just like flow on the solid surfaces, Nusselt formulas will be varied. So there is a great influence of these dimensional numbers to study the and rate of heat transfer in convection, through convection in different channels, just like inner flows and outer flows. It means to flow through cylinders or pipes, flow on the solid surfaces. So we should know about the significance of these parameters. So we'll see first of all significance of the Reynolds number. So this is the Reynolds number. It is represented by RE. In forced convection, so the influence of Reynolds number is very high, because you know that RE is equal to UL by nu. U is the stream velocity or fluid velocity. So in only in forced convection we will see the velocity of the fluid velocity, because in forced convection, so by using some external agent, the molecular momentum will be occurred, just like flow will be occurred through some external agent. So that is called, you know, that is forced convection. So in forced convection, Reynolds number, influence of the Reynolds number is very high. We'll see what is Reynolds number. First of all, what is the significance of the Reynolds number? So you know that this is the ratio of inertia forces to viscous forces. Inertia forces to viscous forces. So in the velocity boundary layer, so that it is used in the only forced convection, because in forced convection the fluid has some velocity, so significant velocity values are there. Okay, so in that velocity boundary layer, so the ratio of inertia forces to viscous forces, that is called Reynolds number. We'll see Reynolds number is equal to inertia forces to viscous forces. Inertia forces nothing but rho into velocity into length. So length of flow. So that is, you know that viscous force is the dynamic viscosity. You know that. Then you know that rho by mu is equal to 1 by nu. Otherwise, mu is equal to mu by rho. So kinematic viscosity is equal to dynamic viscosity by density. So we can rewrite this formula like this one: U alpha into LC by nu. So this is the formula for the Reynolds number. So we'll see one by one the parameters which are included in this formula. So LC is the characteristic length of flow geometry. Suppose the flow is outer flow, it means fluid is flowing on a solid surface, stream velocity u alpha. So fluid is flowing on a solid surface, the length of the solid surface is equal to L. So this is the characteristic length. Okay. So if you consider full length, you have to take the L. If you consider just some distance x, so you have to take the formula u alpha into Lx by nu. So it means length up to particular distance. So it means characteristic length of the flow geometry, it is represented in meters. So sometimes we can take it is the x, a particular distance x. So at x is the distance from the leading edge, starting edge in the flow direction for a flat plate. So it means from the leading edge to a particular distance, so that is called x. So LC sometimes you can take x, sometimes you can take directly full length. So that is LC. Sometimes you will take the LC is nothing but d, diameters. It means so if the flow is the inner flow means so just like fluid is flowing through the some uh, pipe like this one. Just like then L is equal to nothing but to diameter. So how to consider this one? So diameter for a flow through or across a cylinder or sphere. In case of cylinders and spheres, this characteristic length will be equal to diameter of that pipe. Okay. So U alpha infinity is the stream free stream velocity. Units of that one is the meter per second. Okay. So then rho is the fluid density. You know that. So mass of an volume kg by meter cube. So mu is the dynamic viscosity. You know that Newton second per meter square, units of that one. So all are SI units. Okay. So nu is the kinematic viscosity. So it is equal to dynamic viscosity by density. So kinematic viscosity of the fluid, meter square per second. So Reynolds number is a dimensionless quantity because the numerator value units is equal to denominator units. So it means units of mu is equal to units of rho u alpha LC. Rho is the just like mass upon volume LQ. So length upon the time into length. So here LL minus. So here ML minus 1 T minus 1. So this is the units. So that is the units of dynamic viscosity we already saw in previous classes. Okay. So it means dimensionless quantity. Reynolds number is. Okay. So it characterizes the just like type of flow, whether it is laminar flow or turbulent flow. It means by based upon the Reynolds number, we can decide that one is it laminar flow, turbulent flow. So for that one, just like there is some value of the Reynolds number, so that is called critical Reynolds number. So by using that number, we can identify that flow. It means critical Reynolds number for the external flow, just like a flow on a solid surface. The critical Reynolds number value is equal to 5 into 10 to the power of 5. Okay, that if the Reynolds number is less than the, so is less than the 5 into 10 to the power of 5. So that means that shows the that is the laminar flow. Laminar flow. See, the just Reynolds number is greater than the 5 into 10 to the power of 5. So that is called turbulent flow. It means based upon the Reynolds number, we can identify which type of flow. So either it is maybe laminar flow, turbulent flow. So flow identification of the flow is depend upon the Reynolds number. So it means based upon the critical Reynolds number, that is represented by Reynolds number CR, critical value. That is the value is equal to 5 into 10 to the power of 4 for the just like external flow. In case of internal flow, just like in pipes and something, so 2300, that is the value Reynolds number. Here we can see that one. So critical Reynolds number, so CR. So it is the value of just like Reynolds number where boundary layer changes from the laminar to turbulent. So up to 5 into 10 to the power of 5 value. So that is called just like laminar flow. So beyond that value, so that is called just like that is the turbulent flow. Okay, it is represented by Reynolds number critical value. That is the 5 into 10 to the power of 5. Okay, for a flow over a flat plate, so the transition from, so changing from the laminar to turbulent is roughly uh, is occurs just like when critical Reynolds number is equal to, that is the value. It means so if it is greater than, so critical Reynolds number value is greater than or equal to 5 into 10 to the power of 5. Okay. So it means 5 into 10 to the power of 5 is the critical Reynolds number. So less than this one, that is the laminar flow. Greater than this one, that is the turbulent flow. So this is very important. But in case, so this is the formula for the range for the external flow, just like flow on a solid surfaces like this one. But in case of just like pipes, just like cylindrical pipes, inner flow through some pipes, some cylinders. So this Reynolds number RED, so diameter is influencing parameter here. So that value is equal to UL by nu. That is the formula for the just like external flow for the solid surfaces. UD by nu. So for the just like cylindrical pipes or circular pipes. So the formula Reynolds number is equal to U all point D by nu. This value is equal to just like 2300. This value. It means so. So if the Reynolds number is less than 2300, so that is the laminar flow. In case of just like a flow in a inner flow, just like fluid flow in pipes. If the Reynolds number is greater than the 2300, so that shows the turbulent flow. So finally Reynolds values here just like 2300 is the critical Reynolds number REDCR, that is the 2300. It means for the inner flow critical Reynolds number is different. For the external flow critical Reynolds number is equal to 5 into 10 to the power 5. So based upon these critical Reynolds values, we can identify the type of the flow. If you identify the type of the flow, then you can take the formulas regarding that one. Okay. So regarding Nusselt value for the laminar flow, for the turbulent flow is different. You can take that one. You can solve that numerical also. So next one is the Prandtl number. So second number, that is the Prandtl number. We represented by PR. So it is the ratio of, let's see, momentum diffusivity to thermal diffusivity. You know that del by delta T, it is equal to Prandtl to the power of 1 by 3, 0.333. It is related to velocity, thickness of the velocity boundary layer. So this is the thickness of the thermal boundary layer. It means the momentum, that is the velocity related. Okay. So Prandtl number is equal to momentum diffusivity by thermal diffusivity. Momentum diffusivity means it is kinematic viscosity. Thermal diffusivity is equal to alpha. You know that one. Okay. So the formula is equal to uh, just like alpha is equal to so k by mu cp, and just like kinematic viscosity is equal to just is equal to mu by rho. So this is the formula. So if you substitute these formulas, you will get the final value. So Prandtl value is equal to mu cp by k. So that is the value. So mu is the dynamic viscosity, k is the thermal conductivity of the fluid, specific heat of the fluid. This is the formula. The Prandtl number is not given. You can find out this by using these formulas, these parameters. We can find the Prandtl value. So this is the this one also dimensionless property similar to Reynolds number. So it is a function of the temperature. So it provides the measure of relative effectiveness of the momentum and energy transfer in the velocity and the thermal boundary layers also. So this parameter, you know that Prandtl value is equal to del by delta t. So thickness of the boundary layer with respect to velocity, thickness of the boundary layer with respect to thermal. So thermal boundary layer thickness. So that is equal to 0.33. Okay. So this one is the that the Prandtl already explained in previous classes. If the Prandtl number is equal to less than or equal to 1, so uh, what is the condition? What is the significance of just thermal boundary diagrams? We already just like we already discussed in previous classes. So now we'll see the Grashof number GR. So it is represented by just like a GR. So it is used in natural convection merely. We cannot see this one in physical. It means forced convection. In forced convection, we will see the Reynolds number. In natural convection, we will see the Grashof number. Okay. In forced convection, the significance of Reynolds number. So same function will be performed in natural convection by Grashof number. So that is important. It means in forced convection, will solve the Reynolds numbers based upon the Reynolds number value. So we'll identify the which type of flow, either it is laminar or turbulent. So in case of natural convection, so by using the Grashof number values, so by using the Grashof number values, we can identify type of the flow. So either it may be laminar flow or turbulent flow. We'll see. So importance of Grashof number. So it is defined as the ratio of buoyancy forces to the viscous forces. So ratio of buoyancy forces to viscous forces. So buoyancy effect, it means temperature, density differences. So due to the effect of temperature. Okay. So you know that buoyancy effect, it occurs just like casually. Here no need of any external agent to move the particles in the fluid. Okay. So buoyancy forces to viscous forces, so acting in the fluid layers. Okay. It is used in free convection only. So its roles is same as that of the Reynolds number in forced convection. It means in forced convection, so we'll see the Reynolds number. In natural convection, we'll see the Grashof number, GR. Okay, so same functioning will be performed by these two dimensionless numbers in forced convection for the Reynolds number, in natural convection in Grashof number for the Grashof number. So we saw that it is represented by GR. We'll see the formulas of Grashof number value. So you know that Grashof number is equal to buoyancy forces by viscous forces. Okay, so buoyancy forces is equal to G beta into delta T into LC by nu. Viscous force is equal to nu It means no sphere. So it means you know that here G is the acceleration due to gravity. So because uh, due to the gravity effect also influences the buoyancy. So you know that. Next to beta is the coefficient of volumetric expansion. So the formula for the beta is equal to 1 by so TF or T mean. So you know that T mean for the taking of the properties. So we have to find out the T mean or TF is the mean temperature difference is equal to so solid body temperature and fluid temperature by 2. Okay, T mean. So beta is equal to T mean plus 273 kelvins. So you have to convert into degree Celsius into kelvins. So this is the formula for the beta. So next one is the delta T is the temperature difference between the T solid surface to fluid temperature. You know that. So LC is the just like characteristic length you will see. So mu is the kinematic viscosity of the fluid. Kinematic viscosity of the fluid. So this is the formula. So you have to remember this one. G beta delta T LC by mu. So you'll see. So LC, you know that LC in for the external flow, LC for the internal flow. We'll see that one. Okay. So just like LC, you can take that when the flow is passing through different geometrical construction of the body. So first of all, LC is the characteristic length of the body. So that is takes in meters. So first of all, we can see LC is equal to height. Okay. So because in natural convection, height is important. So because of so due to this height is important due to the effect of height and this one. So buoyancy effect, density effect will occur just like automatically less dense particle comes into upward direction, heavy dense particles moves into downward direction. Okay. So you know that LC is equal to height. L is the vertical plate, length of the vertical plate or the cylinders. Okay. So like this one, length. So sometimes we will take LC is equal to diameter D for the horizontal cylinders and the spheres. In case of horizontal cylinders and the spheres, we have to consider the D. So flow in the inner flow, just like flow through the cylinders or spheres. Some cases just like LC is equal to surface area by perimeter, so AS by P for the other geometries. Just like uh, for the vertical plate, we will take length directly. For the cylinders, we will take diameter. So other than this geometries, like other geometries, for that one, we will take the surface area by perimeter value. Right? So here, just like we will use this cross of number in only in the free convection for the transition from the laminar to turbulent. It means so depend upon the value of Grashof number, we can identify the type of the flow. It means laminar flow, turbulent flow. So critical Grashof number value similar to critical Reynolds number, like so GR critical is equal to 10 to the power of 9. Okay, if the value if the Grashof number value is less than the 10 to the power of 9, so that means so laminar flow, greater than, so that is the turbulent flow. So we'll see that one also. This is the significance of the Nusselt formula. You know that last just a few more numbers are there, just like highlighting the important dimensional numbers which are used in the forced convection and the natural convection only. So next one is the Nusselt number. You know that it is represented by Nu. You know the formula HL by K, because it is a ratio of convection heat flux to conduction heat flux, or Q convection by Q Q convection. Okay, so you know that Nu is equal to, you see, just like formula for that one. So gross up number, convection heat flux by conduction heat flux. It means Q by A for the convection is equal to remaining H into delta T. Q by A into conduction phenomena. So that is the value is equal to thermal conductivity into delta T by LC. Okay, ratio of this one, that is called not gross up number. This is called Nusselt number, Nu. Okay. So Ne is equal to, so delta T will be cancelled, HLC by K. So HLC by K. So if you take full length of the solid surface, you can take LC. Other, if you take some distance in the flow direction, so that is represented by Hx by K. Okay, so these are the, we'll see the parameters. So what are the parameters? So delta T, you know that the temperature difference, it means so Ts minus T infinity. So H is the rate of heat transfer coefficient, watt per meter square into Kelvin. So LC is the characteristic length of the fluid flow. Okay. So next K is the thermal conductivity, watt per meter Kelvin. So these are the four dimensional less numbers which are influencing the forced convection and the natural convection to solve the rate of heat transfer. If you know the rate of heat transfer, then you can find out the heat transfer rate. If you know the heat transfer coefficient, if you know the heat transfer coefficient, you can find out the rate of heat transfer. Q is equal to HA into delta T. So finding of H is very important. It is depend upon the Nusselt value, because Nusselt value is equal to HL by K. So in which we have to find out the H value. But Nusselt is associated with the Reynolds value, the function of Reynolds value and the Prandtl number value. So you know that for the laminar flow, N is equal to just like capital C into RE to the power of A, Prandtl to the power of P, PR to the power of P. So for the laminar flow, you know that formula 0.332 into RE to the power of 1 by 2 Prandtl to the power of 1 by 3. So this is for the, if the L is equal to, LC is equal to X at particular distance X. If you take full length, so that means 0. Double of this one, 664 into RE to the power of 1 by 2 Prandtl to the power of 1. So already saw this type of formulas in previous classes. Okay, so based upon this one, we will solve one numerical for understanding the concept of this one, understanding the importance of Reynolds number and Prandtl number and Nusselt number. So for solving of H and the solving of the rate of heat transfer by convection method. Okay, here just like, so small numerical is there. So air at 25 degrees Celsius flows past a flat plate, on a flat plate. So just like this is the flat plate. So this is the length also given. Okay, length is equal to 600 into 300 wide. So length is equal to 600. You can take. Okay, flow velocity U alpha is equal to 2.5 meter per second. Okay, so fluid is like this one. So Ts is equal to 95 degrees Celsius. Fluid temperature T infinity is equal to 25 degrees Celsius. So calculate the heat loss from the plate. So I have to find out the Q value. So you know the formula Q is equal to H area into Ts minus T infinity. So here H is very important. You have to find out the H value. So by using the just like Reynolds and Prandtl values. Okay, so these are the given parameters. You know that. So then you have to find the T mean. T mean is equal to Ts plus T infinity by 2. It means 95 plus 25. So that is the 120. 120 by 2 is equal to 60. So at 60 degrees Celsius for the air, so you have to take the parameters, fluid parameters, it means air parameters. So air properties just like rho, density, thermal and dynamic viscosity, kinematic viscosity, Prandtl number value, thermal conductivity of the air. So all the parameters you have to take by using the data book. Okay. So here parameters are just I'm showing those parameters. So already taken from the data book here. You can see. So take the properties of air at so T mean is equal to 60 degrees Celsius from the data book. So then Prandtl value is equal to 0.696 and just like new thermal conductivity, so is equal to 1897 into 10 to the power of minus 6 meter square per second. Thermal conductivity of the fluid is equal to 0.02896. This is the, so next you have to find out the Reynolds value, because velocity is there means you can identify this is the forced convection. Then you have to find out the Reynolds value. So Reynolds value is equal to U alpha into just like L by kinematic viscosity. So U alpha is given. Uh, it means velocity is also given. Velocity is equal to 2.5 meter per second. So 2.5 into length is equal to 600 mm, 0.6 meters, by kinematic viscosity is equal to 1897 into 10 to the power of minus 6. If you find the Reynolds number, you will get some value. So that is the value is equal to, so this is, it means so 7.91 is equal to 7.91 into 10 to the power of 4. So then how to check this value with the critical Reynolds number. You know that critical Reynolds number is equal to 5 into 10 to the power of 5. So this is less than the 5 into 10 to the power of 5. So you can confirm this one. This is the laminar flow because less than. Okay. So laminar flow, then you have to find the Nusselt value, Nusselt formula. Take the Nusselt formula. So this is which is related with the Reynolds and Prandtl number. So Nusselt for the full length here I am taking. So for full length means 664 into Re to the power of 1 by 2, Prandtl to the power of 1 by 3. You have to take this formula. So you know the value of Reynolds value and you know the Prandtl value also. If you solve this one, you will get the Nusselt value. Nusselt value is equal to 165.252. If you know the Nusselt formula, so then you know that you can find out the H value. So how, so Nusselt L is equal to HL by K. So then you can find out the H. H is equal to Nusselt into thermal conductivity of the fluid air by L. So Nusselt value, you know that too, that is the 165.52 into thermal conductivity. So that is the just like 0.02896 divided by full length is equal to 0.600 mm. So 0.6 meters. So by using this formula, you can find out the H value. So H is equal to that 7.989. So by using, if you find the H value, then automatically you can find out the Q value, rate of heat transfer. Q is equal to HA into, so Ts minus T infinity. So H is equal to 7.989. Area is equal to 0.6 into 0.3. So 300 mm wide, 600 mm length plate. So that is the area into Ts is equal to 95 degrees Celsius to 25 degrees Celsius. So if you solve this one, you will get the answer, that is 100.66 watts. So this is the Q. So in this way, just like you have to find out the rate of heat transfer. So in first unit rate of heat transfer, you find, just you find that one already by this formula HA into Ts minus T infinity. So in first unit, H value and A value, all the parameters are given. So you can simply find that one. It means rate of heat transfer. But in convection units, just like, so you have to find out the H value, rate of heat transfer of the fluid, by using the Reynolds number, Prandtl number, and the Nusselt values. By using that one, you can find out the H value. After that, you can find out the rate of heat transfer. So in this way, just like we can solve the different numericals which are based on the forced convection by using the Reynolds value, Prandtl value. By using the critical Reynolds number, you can identify the which type of the flow, either it is laminar flow, turbulent flow. Okay, we'll solve some few more numericals for the inner flow, just like through cylinders or spheres. We'll see in next class. Thank you for listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.